Thank you very much. And well, I'll try to be brief with everything because there's a lot to talk about. And yeah, that's an advanced topic, and I will try to explain everything, and so that wouldn't be a real problem. I hope, the understanding of things there. The reason why it's advanced topic is that if you're not advanced in Python, you'll have question, okay, why? Why do I need to know that? Because you don't need to know that. So it may be for your curiosity, and that's a great reason. But otherwise, beside that, those things, well, you can make some actual use of that if you are already quite advanced. Okay, about me, my name is Konrad Gawda. I do Python, of course, programming and trainings, but I'm also a cloud evangelist for Orange Polska. And you may ask, what? How come Orange sells SIM cards and maybe fiber, but public cloud? Yes. It turns out Orange has its own public cloud, just like Amazon or Google, just a little bit smaller, and it's located in Poland on our own Orange servers in our data center. If you're interested in more details, it's called integrated computing. Do Google that. And I'm also a host of videocast Porozmawiajmy o chmurze. Check that on YouTube if you're interested. Okay, that's all about me, but the real hero of today's speech is this thing, the bytecode. And I use the green color on purpose to make it more dramatic and to underline that it is hard to understand that because it looks a little bit like assembly language, and it has disadvantages of both Python and assembly language. Yeah, that's true. And so why it's used, where it's used, where does it sit? So let's try to locate bytecode, and here you are a happy Python programmer that uses Python binary to run your Python code. So you you execute Python to run the binary. That's the video cast. Good. And then the result of that is that the Python interpreter does something through input-output with the physical world, like prints on console, uses disk, network, and so on. So that's the real effect of running your code, right? So, but what happens inside this Python binary? There is the CPython interpreter, also called virtual machine, and that's the other meaning of virtual machine, not like the ones you run in a cloud. Okay, so there is the Python interpreter, but before it really kicks into action, there is a CPython compiler that I've also shown the abstract syntax tree there. But compiler, you say, what? Python is not compiled. Okay, it's called compiler, but it's not a real compiler. It only does some kind of parsing of the code so that it's easier to write interpreter that will understand that. And the intermediate step between them, yes, this is the bytecode. So bytecode is some representation of your Python code, of your script, that is pre-parsed or pre-compiled so that interpreter can understand that easily. And it has instructions. There are 122 bytecode instructions in Python 3.13. And it makes sense that I give you a version of Python because this language evolves and changes with each version of Python. And we will have a look at those changes later on. So no, I will not go through all of those instructions right now. No worries about that. Just to show you that, well, there is quite a lot of them, and they look a little bit like those from assembly language. And where is the source of truth? Where are they defined? Well, it's in Python, CPython code, and there is a file called bytecodes.c, and there is a big switch that basically defines them. And this file is quite tricky. If you read comments in it, it turns out it looks like a C switch, but in fact it's not. So there are lots of tricks there. But let's see how it's used, how it works. So let's have some test function. Does this function look good to be used? Okay, so we'll try with that one. So if you know Python a little bit, you know that everything is object. For example, this function is also an object. And most objects do have some dunder fields or dunder methods, so special fields that start with double underscore. And for functions, that's also true, and functions do have dunder code field. And let's explore that. So what's inside? If you type that in your editor and ask for auto-completion, well, those are the names, and I already printed also the values of them for this little function that we use. So, so you see, for example, a name of this function. It's called add. Qual name is also there. There are some methods. They're not. Perhaps replace method will be useful for us later on. But for now, let's forget the methods. Let's see that we have some variable names, A and B, that are used there. Okay. And most importantly, this one. This is the bytecode of this function. So you already know how to get that. Dot dunder code, dot co code. And if you take a list of that, well, those are the numbers. Those are the bytes. This is the code of our function. But okay, it doesn't tell you anything, right? Just raw numbers. So, of course, there are tools to make it readable. And the king of that is this assembler for Python bytecode module called this. Not this, and this. Okay, and it has some functions, so let's explore them. One of them is called show code. And guess what? It doesn't show code. So in fact, it shows you all the other things that you've seen on the previous screen from metadata of this function, but not the real code. This is perhaps why they also have the other name for that, code info. Okay, so that might be interesting and useful, but well, the other thing that every time you read about bytecode, you'll see this function. So is this dot this, and you give it, for example, a function to analyze, and it prints on the console this kind of printout, so like a disassembly. And here you can see the names of the instructions that I've shown before and some other data. So, in fact, what is really important are those things that I've marked in yellow. So, those are instructions and their arguments. Here are the numbers of lines. Those are indexes of those instructions in the raw bytecode. And here are meanings of the arguments. And okay, so you've seen that this function add looks like this. Well, it looks like this in some versions of Python. Yeah, in others it looks different. So basically here you have a comparison for up to 3.6, starting from 3.6, I didn't bother to check out the versions of Python, up to 3.10, it's that one. Then 12 and 11, it's this, and next on are those ones. So for example, you see that there was a binary add operation, and then binary OP with an argument was introduced. Okay, so this is a living standard, and they have also this fancy resume instruction that does nothing, but apparently is needed somehow. Well, yeah. Yeah, that's. If you know why, I guess you can make a separate presentation on this only instruction. Okay, but this method so far only printed on the console. If you really want to play with the bytecode, the better thing is a more Pythonic version of it. .get instructions, and this iterates or gives iterator over objects that represents the individual instructions. So you see the objects, and they have the op name, the number, and also the arguments. So you remember those zeros and ones, they are here, and also explanations. The other part is explanations. What do they really mean? Okay, so you're bytecode experts now, so we can dig deeper. So let's have some more difficult functions to analyze. Okay, you may have an idea what it does. Let's see its bytecode. So it will be in Python 3.12. You have a function, just to remember it here, and here is the raw bytecode. Yeah, but below is the explanation. Okay, so let's see what it. Let's see what are those arguments here. So the function, okay, it uses a instruction load const, so it loads constant, but it has argument 1. So what does it mean? Well, it is a index in the tuple co consts that is attached to the function. So you see that if you use some constants, maybe numbers, maybe strings, maybe tuples, they will be stored somewhere in the function in its fields, and then they will be loaded by the code. Okay, and for now, let's don't bother where it is loaded. What is the target? We'll get to that later on. But this is the source. So you see the argument is just a index, and const loads from co consts. Okay, then it says load global, because we need to use the math module, and it has index 1. So this one is from co names. So load some name from globals, and what will be name? It will be name number 1, so math. Okay.
Is zero math, like zero in that set?
Keep that question. I'll ask you to repeat it a little bit later on. Okay.
If it is 0 on one index, this tuple, like.
But good for that. Okay. So later on, we have load attributes. So from math, we need to take power function, and then again is we use a name that is stored. Then load fast x. What it does, it loads somewhere the value that is under variable x. And again, to take the name x, it uses the tuple co var names. Then again, here store fast is the other way around. So you write into a variable called it's index 1, so it's y. You have the name of the variable, you save something into that. Then again, load fast and return. Okay. Now the question.
Why the conames is one index, not the 0 index? Like the map is the first argument, but it should be
Thank you for that question. Well, if we dig into the documentation, we see that load global and load add, in fact, use inside shift right 1, so basically division by 2, because they use the lowest bit of that argument to store some extra information, some specific Boolean value. I'm not sure what that it really does, but that's the trick to store some additional data there. So that's the answer.
It decides whether to push the null on the stack before or not. That's why this null plus map is here, because the bit is 1, so the null is pushed.
Okay.
I have no idea why this is. I just read this in the documentation 5 seconds ago.
Great to have such an audience here. Okay, but I've made a big effort to keep away the target where it is really loaded. Well, sooner or later we need to talk about that. So how the interpreter really sees the bytecode, what does it do with that? So to talk about that, we need to have the name of frame stack, also called call stack, the evaluation stack or data stack, and there is also a block stack. So how does it look like? If you call some function, it gets a frame. So if there is a function that calls a function, that calls a function, that calls a function, this is represented by stack of frames. So each frame is a context of a function that was called. And inside that frame are evaluation stack and block stack. So evaluation stack, this will be the most interesting for us. This is where the interpreter loads and from the values. So that is the target that I didn't want to talk about previously. Okay, and the block stack, well, it just remembers what are the indentations of blocks that we're going into, just to know if we will be returning from one block or several blocks. So this is, by the way, the reason why they may tell you not to use very many levels of indentation, because that will put another and another value on the stack. Well, some point for optimization. But basically, block stack is not that important for us. The data stack or evaluation stack, this is where the fun goes. So let's go and let's execute this little code of ours, and let's take an argument of 2. So x will be equal to, and we'll go over all of those instructions using our evaluation stack here, which for now is empty. So resume does nothing, so that's already done. Next point is load const. So we call we get to the CO consts and we fetch a value from there, and here we have it. It's loaded on the stack. Then we load something again, and this will be the math module, which is also an object, so a value that can be loaded on a stack. Bam, done. Okay, now something more advanced, because now we'll not just put thing on a stack. The load add will remove that value from stack and push mat.power here. So ready? Go. Okay, done. We've got, so we removed one object that was on top, and we've got its attribute instead on the top. Okay, now load fast the value of variable x. Well, we know that's 2, right? Okay, and now call, and call has only the argument 1, and there is no explanation here, because that's a numeric value. It says that we will call some function and it takes 1 argument. So what the interpreter does is it takes one value from the stack, because here says take one, and that will be argument of a function. Well, which function? Perhaps you guess, yeah, it also, besides arguments, it takes also the next one on the stack, and this will be the function to be called. So in a moment, a new frame will be created for a function, and I will not show that frame, but let's imagine it's somewhere there on the top, and it will eat those two things, and instead it will put from the top a value that is returned by this function. Okay, let's go. Here we have it, it's 4. Okay, so, and the function was called, yeah, we're done with that. Next thing is a binary operator, and it says it's multiply. So we know 5 says multiply. Okay, so binary doesn't mean it's on binary numbers. It says it has 2 arguments. That's the binary operation. 2 arguments and multiply. So if two arguments, then it will remove both of them and instead put on a stack the result. Let's go. Well, done. Okay, the next one is store fast. So that one will remove the value and save it under the name y. Poof, it's gone. Okay, and that was one line of code. But we need to do the next line, which says, again, load fast. So we have our value inside the variable. Now we need to load it from the variable into our stack. So load fast, done. And then the final act of our masterpiece is to return the value that we have on the stack. Done. Okay, so that was bytecode. Easy, right? Okay, so so we know the idea behind bytecode, and what's about those PYC files? Well, in this whole process, they're here. So a Python binary saves this intermediate step to save work. If you don't change your code, then run it in again. You don't need to run that part. And PYC files, they're also called cache files. They have this kind of structure that they have some magic number, bit field, timestamp, and timestamp of the source and size of the source. So that this is where you know if the PYC file is up to date. By the way, there is also another format of that. It differs with the bit field value that instead of timestamp and size has a hash value, but that's not quite used from what I know. Okay, what's the magic number? Well, I've said that this language differs from Python version to Python version. So each Python version has its own magic number with a quirky way of deciding the value. That's a fun thing, but not really useful. Just to remember that there is a magic number in the PYC files telling you or telling the interpreter what was the version of Python, not to confuse because there are different languages inside, let's say. Okay, when those files are created? Well, they're created on import. So if you, inside your Python code, if you import something, that will create and save that file, but also on pip install if you install some package. And the standard library comes with PYC files ready. Okay, but if you'd like, you can also create them manually. And there are 2 commands. Command for a single file and multiple files or directory. And then it will recursively go through whole directory. So, okay, let's test that. So I say compile all and give it just one file. Could give more. It says compiling. Okay, it creates PyCache directory, and there is a shining new PYC file. Fun thing about those files, you could also ask Python to run them directly. And yes, it does. Okay, and you see that the name of the version CPython and its version is there in the file name, just to make it simpler to find it. And what are the takeaways from that part? Avoid unneeded imports, because it will on some step need to save the file on the disk. If you don't need to import, well, don't do, will be a small optimization. The other thing that perhaps that's the most practical thing of the whole speech. If you're preparing your application in a Docker container and you're not installing package, just putting your code there to be executed, consider adding in your Docker file python -m compile all dot. So just in everything from the current directory recursively compile that. And then each time you run your container, Python interpreter will have one less or many less steps to do, depending on how many files you have there. So that's my trick. I do that. Okay, but I've talked about that format, and I've said about the top, and then what's really inside those PYC files? What is the bulk value there? This is just a content of your file in a Marshall format. Well, if you go to documentation, it says this format is undocumented on purpose. And it might change between versions. Well, we know already that. But there is a module to analyze that, or just to perhaps load and save that. So if I take a file, I need to skip the header, and then I can load the data. And in fact, it only has one thing there inside it. It has a module. So the file that you write, in fact, is an object of a module type that then can be executed. So, well, for me, it's a quite fresh thing to look from this point of view on the files that I write. They're basically objects created in that way. Okay, some small useful things. In the step of creating bytecode, there is something called optimization. And you could, well, when compile all, you can ask for several steps of levels of optimization. It will generate several files. And what are those levels? -1 is default, 0, which in fact typically is the default, is no optimization, and debug is true. Then 1 removes asserts. So if your code depends on assert keywords, well, beware of optimization. And it also sets debug to false. Level 2 also removes doc strings. And in fact, you can also run Python directly with those optimization levels. Well, good to know, especially if you rely on asserts in your code. That was one handy function thing. The other one is exception handling. If you have a really pesky source of exception, like let's have a exception here, you could just run this without arguments. It will dig into the last exception that was raised and show you the printout. You can also say this.thisTB, like for traceback, and give it a specific traceback object. Well, perhaps maybe useful one day. Okay. I've said bytecode changed over years. I'm not gonna spend much time on that, but just to have a quick look, here you have a comparison. What were the different operations available in 3.01 up to 14 release candidate? So this shows you that it was changing. It was evolving. I think if you're interested in details, we can look at that after the presentation. You see that 3.11 did some serious cut there. Okay, but the one also thing changed in 3.11. Remember that function? I told you in 3.11 it looked like that. Well, there is one small trick, bytecode instruction specialization, which you can look into by adding adaptive equals true. But it's the same code. Okay, so what's the fun here? Well, if you use that function in question, so the add function, the adaptive code changes. So I use it 2 times with integers. It changes the instruction to binary operation add integer. It doesn't break anything, it only optimizes it. So then again, I can use it with other variable types, like I use it with floats. It is less efficient, but I use it 50 something times and it switches to binary operation add float. So since adding of those instruction specializations, your code may speed up after running several times. Good to remember. Okay. I think we'll fit that in very quickly because I wanted to show one thing that is not so useful, but for me it's very cool. Let's try modifying functions on the fly during runtime. So if you dig into documentations, you could see that it's not for faint of heart. Yeah, in fact, we'll not use the code class, we'll use the function type. So we will create new functions. And it works like that. You give it code, and I guess that was globals. So, okay. So I create a function that is exactly the same as add was. I'm giving it the code of add. And I try to run it, and oops, I forgot the arguments, A and B, of course. So I add them, and I've got the result. Okay, that works. That's the same function. Same as like in strings, I can also do replace on the code. And here is empty replace, so that doesn't change anything. Same here. But I can replace, for example, the variable names. And instead of A and B, give it X and Y. And oops, I forgot to give it arguments, but it says, you forgot about X and Y. Seems to work. And giving it a proper arguments, okay, it works. So let's do something more serious. Like, you remember that was the bytecode that I've shown you? Well, let's have some fun and change one of those numbers. In fact, I did the math. This changes the operation instead of adding, but I don't know what does it do. And remember, it was 5. 2 plus 3, that's 5. And now it's 2. Okay, but what the hell would be that? 2, some operation 3 gives me 2. Okay, so we can check other values. So I'll give it a loop and I'll just give it next and next value from 0, 1, and so on. Let's see. Well, so 5, that was for 0, 2 that we had here, some 0, 16, and matrix multiplication opcode was removed in this Excel file. Okay, but you've got the at or Maupa or Klammeraffe in German. Yeah, so that would be our monkey here. Okay, so that would be 0, 1, 2, 3. So number 4 stands for monkey here. Okay, and let's go a little bit forward. So that's the same code. I've just silenced the exceptions. So this is unsupported operand, and then well, a little bit of different types. Also, you can see the monkey equals here. So you see that those kinds of operators are also here. Okay. If you would like to guess, that's the last moment. So make your wish. Think what kind of operator was that, because on the next slide, bang, we'll get that. And so, okay, the under index 1 was the ampersand operator. So binary AND. And that was the result of giving you 2, but also modulo would give you 2, so the percent sign. And in fact, I used here the dist.get instructions and then the argrepr to get what was the real argument there. So you can do that. You can change functions and their behavior on the fly. People did use that to make f-strings before f-strings were a thing. But nowadays, well, if you have an idea, go with that. But otherwise, don't bother. Just remember that bytecode is there, and remember about .pyc files. That's it. Thank you very much. That's the venue code if you'd like to check in. Yeah, and if you have any questions, well, that's a proper moment. And that's your first.
Do you use this in practice? For some reason?
Okay, there are people who do, I see it. Okay, I did once to see myself why they say that different ways of creating dicts, one is faster than another. I used that in real life once, and the only one. Okay, let's go row further.
About using it, like I had situation in the work Friday when there was I done rendering in Python, and then there was in Blender some scenes from the frames that were using bytecode instead of in the JSON instead of the normal value. So I just wanted to ask if you maybe know where is this moment and why they were using like bytecode instead of like normal value in JSON, because in Blender it's pretty often.
You mean that in Blender they were inside JSON, they were
Yes.
storing bytecode,
Yes.
like row numbers?
Like B and C, and I had to like resolve this problem, but it was some quite like technical.
One way why people do use PYC files is some kind of obfuscation. There are disassembler modules that can translate the code quite well back into normal Python. That could be one reason. Or the other reason, I guess perhaps it was for logistics, that it was shorter to put into JSON instead of real Python code. But well, I mean, that can be lots of trouble. Python version changes, breaks everything. So, well, strange. Okay.
About some uses, I know of a very interesting one, particularly very similar to what you've shown with constructing functions manually. How many of you know async.io? Oh, okay, so that's some amount of people. And did you know that besides the normal REPL, so the console that you open up and can put some instructions and get the results, there's also a dedicated async.io REPL. And during the way that it works is the async.io REPL allows you to not use async.io run to run coroutines. And instead, there is a flag that the CPython compiler can take and allow top-level await expressions. And then it creates a code object that can be used to put into into a function, and then it will work like a typical coroutine function. And it is used in the async.io REPL to get your instructions, construct coroutine functions, and then the entire event loop management happens without you even knowing that. So you can like create async, you can like do awaits directly, and you don't have to use async.io run to run that.
Wow, that's great. People do that. I mean, well, I love Python community.
Yeah.
Okay. Yeah. Next
And
question.
Actually, it's supported in Python upstream. It's not an external package.
Ah.
Yeah,
Okay.
You can do python-m async.io and it will run async.io REPL.
Okay. If that was not recorded, I will repeat that just for the rest of the humanity that is listening. That if you do Python -m async.io, it opens a async.io REPL that uses this kind of tricks. Well, great.
Yeah, that's very cool.
Right. Okay. The next question will be here.
Do you know if in the case of code debugging, do we have debugging symbols added to the bytecode, like it's in, for instance, in C++?
Yes.
Yes. Yes, we. So the answer was yes. We do have debugging symbols in case of interactive debugging. That was the question. Interactive.
Yes, in
Yeah.
the case of debugger.
Debugger. Okay, great to have you guys. Next question there.
Can you navigate back to this slide where we were navigating through the bytecode from the one?
You mean the slide where we were using the code going through the...
Yeah, exactly this one.
Yeah.
So my question is about these numbers on the left, like 2, 4, 14, and so on. I guess these numbers are offsets into the byte string of the function by the particularities.
Exactly.
So the question is, why is the low touch without instruction so big? It's like 20 bytes for just loading for nothing.
Uh-huh. Well, good question. So yeah, if I would really was forced to answer that right now, I would just open the documentation for the this module, which has also a documentation of each instruction, and apparently there would be something about that. My guess is right now is that it's able to store a lot of arguments. That's my guess. Okay, next question there.
Okay, so you said that pip install is actually precompiling the dependencies that it installs. So a word of caution for people that use UV. UV is by default not compiling PyWaw files.
Oh, okay. Okay.
Because they basically assume that you first install dependencies, then you run your code. So if you want to put it in something like Docker, which we also mentioned, then you should precompile your files. It will then happen on runtime.
Okay, UV doesn't precompile those files, just like normal Python would. Okay, good to know. Thank you very much, sir. Okay, next question was there.
Yeah, I have a question with the same slide. Line 48 and 50, store fast and load fast. Couldn't we optimize this? And why wasn't it optimized by the optimizer? Because you use this local variable. We would call this local in C only for returning the value. So shouldn't we write it without y equals and the value would, isn't it faster?
You mean to skip using this y value?
Yeah, exactly.
Yeah, that's so perhaps PyPy would do that. And okay, I guess there are tricks in the new versions of Python, but just this shows the idea of bytecode. It's not that smart. It only parses. It's only effect of parsing the code and perhaps skipping some really like multiplications of two constants. If those two will be constant, then okay, it would replace that. But otherwise, it sticks to the structure of the code.
Yeah, I have a query for people interested in multi-threading. there's also the GIL-free build. But with the GIL, the difference here between returning it immediately and assigning first a variable and then returning a variable and like getting it back is that there can happen a preemptive switch between those instructions, bytecode instructions, because as far as you know, with the GIL, multi-threading works like between particular bytecode instructions, the interpreter can switch to a different thread and execute some other code and switch again and again and again. So here the difference would be that if you wrote it like return free point, like the pi times the power, the difference would be that there's less room for Python to switch between threads. So that's just
I just wanted to ask if you have disabled optimization just for didactic purpose, or it's not that's marked by default.
Yeah, but just to remember, because there are different meanings, but optimization, the default meaning is those optimization level 1, 2, 3. They wouldn't do that. They only set debug to false. They skip asserts and they skip docstrings. That's all this type of optimization does. Okay, do we have some more time for questions?
I think next question should be all private soon. Okay, we need to finish now. So thank you very much.